Okay, let's say we have a really interesting conservation problem. Let's say we have like a ball right here on this ramp. And this ball is going to start at rest. We can start it however we'd like. And it's going to roll down this ramp. So this ramp, it has a height. Let's call that, let's say that that height is 1 meter. Okay. And it's going to roll down. Well, that's actually too high. There's no way that's 1 meter. Let's say it's 0.2 meters. Okay? And it's going to roll down this ramp, but it starts at rest. So at this point, let's call this point A. Our velocity at A is going to be 0. Okay? And let's even define this even further, that this right here, this distance from here to here, well, that's going to be a height of, I don't know, how tall is a desk? Maybe like 1 meter. That seems practical. And it starts here at point A. And it's going to roll down this ramp, down here, onto the desk and off to the side. And you may want to ask yourself, well, how fast is this object traveling when it reaches, let's say, let's give ourselves a couple points. Let's go point B, and we're also going to have point C. And the only way, well, not the only way, but the best way to solve this is conservation of energy. So I want to find VB and VC. This may seem like absolutely crazy, but conservation of energy allows us to make these calculations. They're not the most simple, but they're pretty eloquent. So remember, if I know that energy is conserved, that means that energy throughout this is going to stay the same. So ETA equals ETB equals ETC. I mean, I can really easily do this. Now let's talk real quick. When might energy not be conserved? Well, that's when we're going to have an exterior force that's not gravity. So if you have another force that's not gravity, like maybe friction or maybe like a magnetic force, even in a magnetic force we might be able to account for. But energy, in this simple sense, will not be conserved. So that's something to note. So please note right now that if we have this other exterior force other than gravity, we're going to have some problems. Okay, but we do not, so we will move forward. So let's take a look at our situation A. Now, one thing I really want to stress is it doesn't even really matter what the mass of the object is because it's going to cancel out. So remember, ETA is, our energy is found, this energy has two pieces. It's going to be our KEA plus our PEA. And that's going to equal, we can just do this first one first, KEB plus PEB. And we can write these formulas out even further because you guys know that they are actually made of things. 1/2 mVA squared plus mgh A equals 1/2 mVb squared plus mgh B. Awesome. And we can substitute this in and what values we know. Now, the thing to realize about height A is that it's a meter plus 1, which is going to give you 1.2 meters. And I'm going to cancel out all my m's too. Don't forget about doing that. That's always a fun thing. Remember, this guy goes away, and this guy goes away, and this guy goes away, and even this guy goes away. So you're left with 1/2. Remember, we said we started from rest. 0. I'm going to leave off my units for this, well, that one, because it's 0. Plus, I'm going to leave off all my units today, guys. Please don't yell at me. But I'm just not in the mood. 1.2. Now, I got that 1.2 again, guys, once again, because this is 1 meter, and this is 0.2 meters. And to get the actual height of A, it's 1.2 equals 1/2 VB squared plus G. I know sorry. Control Z equals 1/2 VB squared plus 9.81 times 1. Okay. And this shouldn't be too bad. You should realize that, once again, this term's going to cancel out. And you get 9.8 times 1.2. Oh, I don't have my calculator near me. Come on. We'll do it here. Excel, my good friend. I'll show you so you can see all the work. So I'm just going to pick a cell. Equals 1.2. Let's get this out of the way. Times 9.81. Enter. Okay. So that's going to be 11. It look like 7.2. Up. Don't do that. 11.772 equals 1/2 VB squared plus 9.81. Now I'm going to subtract. I'm just going to come back here. I'm going to go equals this minus 9.81. Enter. And I get 1.962. So I'm subtracting this from both sides, and I get 1.962 equals 1/2 VB squared. And now I'm going to multiply both sides by 2 equals this multiplied by 2. And you get 39.24, or 3.924, I'm sorry. Let's scroll down. 3.924. And that's going to be, actually, if I want to put the units there, meters second squared equals VB squared. Now I need to take the square root. And taking the square root is pretty easy on this. So you just go equals this, and I'm going to put the caret to the 0.5, and that's the same thing as square root. And enter, and there we go. We get a velocity at that point of about VB equals to 1.98. Or yeah, 1.98. We'll just leave it at that. Meters per second. Okay. So let's go back up here and look at this. So I have a velocity at B. Let's use one of our arrows. We have these for a reason. We have a velocity of B of equal to 1.98 meters per second. And the interesting thing, guys, is this is our x velocity. And this is going to roll off this edge, and it's going to hit the ground down here. But there's a pretty simple way of calculating the velocity that it hits the ground with, and that's going to be conservation of energy. I'm going to get another blank sheet from over here off the screen. My documents. Let's rename this. Rename. Blank. Enter. And I'm going to bring that over here. So now we have a new blank document to work with. And now I'm going to find my velocity at point C. I could find some interesting things at C. And we will see. So remember my ET A equals ETB also equals ETC, so I don't really need to do anything different. And I'm just going to go back over here, and you see that I found this value right here. This value right here is actually the velocity. That's my energy on the left. And even though it's my incomplete energy, because I did multiply by mass, I'm just going to use it over here. I'm going to go 11.772 equals 1/2 mvc squared plus mghc. Now, something interesting, though, to go back and look at this, you'll see that at point C we have a height of 0. We're nowhere near. We're on the ground. Sorry, we are on the ground. So that cancels that out. So this whole term goes away. And what we're left with is 11.772 equals 1/2 mvc. Oh, sorry, this m cancels out. Oh, geesh. I shouldn't have m's here at all. Squared. Sorry. The reason the m should be canceled out is because I don't have an m on this side. I've already taken the m out of this side. This value actually should be multiplied by m, but then I cancel that out. Okay, so we're ready to rock. I'm ready to do some Excel calculations again. Let's see them. So I'll put it right here. That's not what I want. So I'm just going to start right here. I've got 11.772 And then now I'm going to multiply that by 2, so I'm going to go equals this multiplied by 2, because that's how I'm getting rid of my 1/2. 1/2 right here, can multiply both sides by 2, and I have to take the square root. Raise it to the 0.5. And there you go. And that is my velocity at point C. Okay, so there's a lot of cool things we can solve for here because we have, the interesting thing is if we go back and look at our original document, we'll see that we have the x velocity right here. This is actually your vx that it leaves the table with, and you just solve for, right now, its velocity right here. You solved for our vf. Well, this velocity, if you take these two, you should be able to find your vyf as well, because remember, this vx stays the same. Right here, you should have the same vx. And right here, that's not an x. Right here, you should have the same vx as well. And then maybe you can use these two vectors to find your vy. Or a lot of different things, guys. This opens up a lot more possibilities. It's a new tool. It's kind of like your new Batarang. Okay, good.